Welcome to this course, Introduction to the Java Language. I am your instructor. My name is Jim Sullivan. This course is a presentation of coding boot camps. There are no prerequisites for this course. For our first session, let's take a look at the fundamentals of the programming development lifecycle. For our audience here, are those that are new to software development and those interested in computer science. So our objectives here are going to be to learn a little bit about the computer and to discuss algorithms, the difference between source code and machine code, our design, compile, and runtime, software program architecture, and then we're also going to look at integrated development environments. The materials you'll need are just the slides that are presented during this session. So a little bit about computer architecture. Well, there's a lot. This is a broad topic in and of itself, but let's say for here, computer architecture is going to be the set of rules that describe some kind of a functionality, something that will deliver a computer program for us or do some computing for us, follow some rules for us. And also the architecture describes the capabilities of our programming model for our computer. So that's going to be for our case here. And there is an abstract model of computing that's seen by machine language. And machine language really is what runs on the processor for the computer. Maybe you've heard the term CPU. The CPU is a chip. If we were able to look down into a chip, we would see a set of conductors or something that looks like wires, and voltage travels on those wires. And that is really what's going on. As those voltages represent data, and the data is actually processed by our computer. So there obviously is a computer is quite a complex system. So we have the chip, which is the heart of the computer, but we also have the disk, the memory, the monitor, the keyboard. So all of these system designs go into our overall computer architecture, computing architecture. Intel or x86 is one popular computer architecture, and that's the PC, or our typical laptop. Anything that Windows runs on is almost always at least modeled after the Intel computer architecture. So it's giving us that system design that we're so used to with the mouse, the screen, the speakers, etc. For Java, the good news is that we don't really have to worry too much about computer architecture. At one time you did. At one time, anytime that we were engaged in some kind of a programming task, we had to know a lot about the hardware, how the hardware stored the data, how the hardware processed data, how the hardware read data. And that was a big part. And a lot that made programming quite complex, but also it made it less portable because you had to have different versions of the same program to run on different hardware, so it was not very efficient. Here, as we can see that we actually have our Java code. If we look here, we have our Java code, which is what the programmers are going to be concerned with. And also the compiler as well, because we have to make sure that our code compiles. But if we take a look down here, there is a special program called the JVM, or the Java Virtual Machine. And what the Java Virtual Machine is able to do is able to map different hardware back to the bytecode, the compiler, and up to my source code. So that way, no matter what happens, I can write the same Java application using the same source code. The Java virtual machine will map all of that for the individual hardware. So I have to have the Java virtual machine installed first, and then I actually run my compiler and I build my Java source code on top of that. You may have also heard the term algorithm. An algorithm is a very important term in computer programming. Let's just say algorithm. The word algorithm means solution. So in our case, it's going to be the steps performed to get to a particular solution or to satisfy a requirement. You can see here it says sequence of actions, calculations. All this is true. But really what we want to do is come up with a way, a generic set of rules that when a particular program is written, that those rules are invoked by, say, Java or .NET, and those same business requirements are completed. So an algorithm is the steps to satisfy a requirement or to deliver a solution. And algorithms really are the essential way that the actions to get to the solution are performed. So we hear a lot about, particularly in the finance market, based on market conditions, there are certain algorithms. And really what's happening there is there are a set of steps that the computers are running. They are testing for conditions. If those market conditions exist, or if they are true, they will possibly sell some shares, or they will possibly buy some shares. So again, it's executing and testing some kind of a step and in order to satisfy some kind of a business requirement. Same idea here with calculating employee paychecks. There are a set of rules. There are a set of business rules that a person could do, but we don't always want a person to do it. We want the computer to do a lot of the work for us. So we will actually define those rules and then build a program that actually implements those rules. And also with calculating report cards and printing report cards, we have to identify the business process and the business steps, and then we can actually line by line. Sometimes it doesn't always have to be line by line, but we will set up a program, in this case in Java, to calculate and print those student report cards. So here's an example here of an algorithm. So our requirement in this case is given a list of positive numbers, return the largest number in the list. And this is a way a lot of times an algorithm is written. It's written in something called pseudocode, and this is pseudocode, meaning it looks like a programming language, line by line, and line by line it often will match up pretty closely to most computing languages. However, it's very generic, so it can be moved, so our algorithm or pseudocode here can be moved to our programming language of choice, Java or .NET. So right here, we're defining some kind of a list. So however that's done in our computer program of choice, we're initializing our variable here called max, and then we're moving through this list. So what it's doing, it's looking, and then it is looking at each member of the list, and if the next member is greater than the current member, it moves the current member to the max, and then it will go through the list and it will return the maximum number. So source code versus machine code. So interestingly enough, source code is written for programmers, for people. And so it has a lot of qualities that make it very understandable. Machine code is very hard for people to understand. It's meant to be run on the processor. It is very, very low level. So very fundamental tasks are completed by machine code. So quite often, and most of the time, source code, one line of source code can match several lines of machine code. We'll just say several lines because it's not always clear what the ratio is. And essentially, source code is compiled ultimately or broken down into the machine code, which will run on the chip. And we saw an example a little bit earlier of that Java virtual machine. That along with the Java virtual machine and the compiler, the source code, the Java code, will be taken and compiled into the machine code for the Java virtual machine. Then it will be further compiled down to code that can execute on that machine's chip. So if it's Windows or Linux or I think we saw Mac OS. So that is the idea with source code versus machine code. The machine code is really just ones and zeros ultimately, whereas source code is going to be commands, keywords, structures, data, and other things. So again, machine code is a set of instructions executed directly by the computer's CPU or processor, and individual tasks are run, and almost all practical programs today are written in higher level languages, and that source code is compiled into machine code. That's absolutely true. Here we can see an example. We can see here there is source code here, and there's just a few lines of source code here. However, we can see here when compiled ultimately into machine code that will run on this machine, we're going to get many more lines of machine code than we have source code. And this is not even the lowest level yet. It actually, something like Java will go through different iterations getting down to ultimately the ones and zeros that run on the processor. And compile time versus runtime. Let's just say this is design time, compile time versus runtime. So design and compile time runs, that refers to the operations that are performed in the editor and in the compiler. So what will happen then is the compiler will take the statements of the higher level language, will go through its set of tasks to convert it to the machine code or the bytecode. Many times there are errors. Sometimes there are syntax errors. Sometimes there are runtime errors that it will be able to identify for us, and then we will get back compile errors. And the compile errors mostly are syntax errors. Will usually be indicated clearly what's wrong. Sometimes it will take some troubleshooting. And the idea is that the compiler was not able to take the source code and convert it into the machine code. So some kind of a rule was not followed in order to convert that source code into something that can eventually be run on your machine's CPU. And we can see here the design time versus runtime. You can see here that, well, in this case, everything did compile, and we're actually running our program here. But during the run, during the execution, we encountered an error. Division by 0, that's what it looks like here. That's a pretty typical runtime error. But as you can see here, that there will be times where even when you're, though you've got the code to compile, you still can run into an error during execution. And thanks to networking, we are able to scale up our applications using something called architecture. And architectures are made possible again by networking. It allows for many users and remote services to be used, and it increases the number of users, like we just said, but it also increases the speed, and we're able to reuse a lot of different services. The standalone, that is the simplest type of architecture. That's where no external services are used at all. Everything that's running was written on the machine, and the machine is the runtime environment. and that runtime environment is not using any services other than what is available on the machine itself. So that is the simplest architecture. Client server became popular several, I guess, decades now, and it's an architecture where we have a client which is making requests to another application called the server, and they are the client makes a request or sends data to the server. The server processes that data that's sent down or that request that's sent down, and then sends results back. So and again, the communication is over the network. And this is a good example. So the web browser is the client, and the website you visit is the server, and you're making requests with your browser, and the server is responding to those requests and sending back data. Distributed is a variation of that. It's a model located on network computers. So we are able to use services on different parts of the network. And again, we can reuse a lot of those services. And quite often those services can be specialized. And then our web-enabled are a specialized set of distributed computing using web technology, or let's just say using a web architecture where we have a special application called a web server or web application server, and we're also using a database. So if we look here again at the standalone, this application here is running, and it's only using what's available on the runtime machine where we are running it. Here is an example of client server. We have the client here running locally on the machine. If we look behind the scenes, we could see that when we click this submit, all of the processing is being done by a different machine. So the data is being sent over the network to another application called the server. It's taking the request of the client, processing the data, and then sending back the results. And the results then are displayed on the client. And this is our web architecture. So you could say the web is a specialized distributed type of architecture. Web client here is a browser almost always. There certainly can be exceptions to that. We have our server, which is listening for the requests and application code. The application code is actually extending what's available from the server. And then we have the database. No data is actually saved on the server. It's runtime only. All data is saved in the database. So the application code is responding to requests sent to the server, and it's actually querying or maybe updating data in the database. Using data in the database to build pages, which are ultimately sent back by the server to the user to view in the browser. And again, here is an example of our web architecture. We can see here our source code, and we can see our browser in here, and that is a browser. It's just embedded in this in this window here. There is a server running behind the scenes. You can see it down here. Just a mention here of the server, and you can see here the response and the data that is getting written back to the browser, ultimately from the database, but is getting written by the server. So the browser is actually making the requests from the user. And our interactive development environment is a specialized application, a standalone application that runs on our desktop. It gives us tools to make computer programming less difficult. Notice I'm saying less difficult because it still is a difficult task to build software or to code an application. But our IDE certainly can give us a lot of tools such as syntax highlighting, a nice editor environment, local build automations, and a visual debugger. So our debugger helps us, when we have a problem, go step by step through our applications to identify where we might have an error. There are all different flavors of IDEs. IDE stands for, again, Integrated Development Environment. Some are free, and there are some that are commercial software. So they are, you have to actually purchase a license for them. Here's one example of an interactive development environment. This is called Eclipse. And here with this environment, this is what we will be doing all of our examples. This is what we'll be using for all our examples. It does a nice job. We can see here the syntax highlighting, and it will give us some tips as we go through. It allows us to view our structure through an outline. So it makes our just gives us a lot of rich set of tools, a very visual set of tools, just to make our programming task again less difficult. So for our assignment, let's think about algorithms. What is a solution, or what is a requirement, and what are going to be the steps that we need to put together, which will give us a solution? So we can think in this way, we can think, well, what are the steps to get to the grocery store, from our home to our grocery store? We can get as detailed with the steps as you think you need, or we can be high level. You can say, well, I just make a left on the street, I go a mile, I make a right, and I park the car. Again, we could break that down into other steps as well. So just think about, though, in general, what are the steps to satisfy a requirement? And let's break those steps down as low level as we think we need. And we can start to get an idea, okay, this is what the computer is going to be doing for us. So here we learned a little bit about the computer and the hardware, and we talked about algorithms. We talked about the difference between source code and machine code. So remember, our source code is what the programmers use, and our machine code is what the computer actually uses. We talked about compile time and design time versus runtime. And we talked about software architectures. So our different application architectures, such as standalone, such as client server, such as web. And we looked at integrated development environments or interactive development environments. There are live private coaching sessions available for Java. So in your materials, obviously you can't click on this recording here, but here are the links to get information on tutoring sessions and tutoring sessions for the Java programming language. So thank you for watching this session, and please watch the next session.